Okay, so we have this working for add I, sub, and sub I. Um, let's go look at our list. So tell me, how do we have loads and stores, right? How does a load work and how does a store work? What does load do? Okay, so load is how we get stuff into a register from memory. Store is the opposite, right? How do we get something from a register into memory? So then how do we represent our memory? So we have a tab here, right, for our RAM. How are we going to represent RAM here? We have to kind of think about, go ahead. So if we look at the book had a, oh, I'm sorry, I'm scrolling all the way through the, yeah, here's the simulator. So something along the lines of this. So we have these memory addresses, and we can just give it a base address for starting. If I say 2000, does that let us go back? Okay. How far does it let us go back? Can we show memory address 0? All right, so this guy's effectively an array. All right, so he's an array that's showing a bunch of memory addresses. So what we can maybe do, we can decide what's the, now for this, are they making an assumption? Is each of these addresses, is this 1 byte? Is this another byte? Is this another byte? I wonder if how they're, so they're storing like a 30 there. Wonder how they're treating, because if I show memory address 1. Okay, yeah. So this is everything that lives in memory address 0 to 7. So that's a byte, correct? All right, and then so we're doing bite-sized chunks if we want to mimic this. So what we would maybe have is we would maybe have what kind of range do you think we need for our simulator? How many bytes of memory do we want to represent? Debate that while I take a bite. Pun intended. Pause. Hear me chomping. So assume like we're storing an array. So if this is, if I want to show memory address, so what we have right here is effectively a array with 2 bytes in it that has a base address of 0. So bucket 0 of that guy has a 5 in it. Bucket 1 of that guy has a 7 in it. That's how we're representing memory in 1 byte chunks right now. So we can create something like this and maybe give ourselves 32 bytes. I mean, really, almost anything will probably work for our little testing. I'm thinking of something maybe more like, because typically you want memory. Typically, memory is a bigger location that's slower, right? So when we think about the different kinds of memory that's in our computer, registers should be very small but very fast. Now, in real life, our registers, we'd have like 32 registers in ARM, and then maybe you would have, maybe call it 1 gigabyte of RAM. Probably, okay, so if we say 32, we'll say 1024 divided by 32. So we have 32 times more RAM than we have registers. We just kind of operate off of that. So that means if we have 8, we should have 256 bytes of, because we currently have 8 registers that we're mimicking. So we'll have a 256 bytes of RAM. Okay. And we want to represent this on our RAM screen here as something that maybe kind of looks like this, but we should be able to scroll through and then change values at individual buckets. So what I'm going to do is I'm going to put a scroll view in here. And then inside that scroll view, I want to put edit texts. So I'm going to have a list of edit texts in a scroll view. So we're going to have to build that, and we want to have, if each one's going to be a byte, I'm going to have 256 of those edit texts. So what I'm going to do here, we'll go into, I need to bring my layout back open. Here's my RAM one. All right, so I'll get rid of that thing there. I'll go ahead and put my, actually, I'll just put my scroll view. I'm actually going to still give myself my vertical linear layout. All right, so there's my vertical linear layout. I'm going to give myself a button at the top to save. So this will be my save button, kind of like we have our registers. And then underneath that, I'm going to put a scroll view. All right, so here's my scroll view, and this guy has a vertical linear layout in it. I'm going to name my scroll view memory. Actually, I'm not going to name the scroll view. I'm going to name the linear layout that's in it. This is going to be memory. Called memory layout. All right, I want to give myself access to that guy. That guy's going to be a view group. All right, so I'm going to give myself programmatic access to this view group, and then I'm going to go through and I'm going to fill this up with 256 edit texts. Okay? Let's see where we at here. I'm lost. Oh, I don't have my memory screen open yet. RAM activity. There we go. Okay, so I'm going to go ahead. I'm going to give myself a private edit text array up here called the memory. All right, then inside here I'll say this dot the memory is equal to a new edit text array of size 256. So I'm going to have 256 edit texts. All right, now I also need to give myself access to that view group. So I'm going to say view group memory VG. Actually, what did I call it out there? Memory layout. Is equal to the view group version of this dot find view by ID r dot ID dot memory layout. Okay, so now I have access to that guy. So now I want to say for int I is equal to 0, I is less than 256, I plus plus. I want to create a bunch of edit texts and throw them into that array. So I'll give myself a little, I'll do an edit text temp. So we'll say temp is equal to a new edit text. And I believe this guy requires a context. What else does he need? Is that it? Maybe just the context. All right, and then I'm going to say temp dot set hint. I'll just say enter a byte, that way we can see something in it initially. All right, and then I'll go ahead and I'm going to say memory layout dot add view, and the view we're going to add is going to be temp. All right. So this should, and that's a vertical linear layout, so we should just keep adding edit text, and it should be scrollable because it's inside that scroll view. All right. So let's go check this. I'll just move away from the microphone.
Don't know what it is. Come on, man.
He wouldn't have been able to do it that fast. I'm old, but I program fairly quickly. It was nice when I was in my 20s. Now you just don't care anymore. You kind of feel like you're like I probably feel kind of like Michael Jordan feels now.
Okay.
You know, like like you know, he used to be so great at basketball, so now it just doesn't matter. He spends all of his time on the golf course or in Vegas. I think the harder skill to learn for a programmer is to do live programming in front of groups and not make tons of mistakes and be able to also talk while you're also thinking. I think that's the harder thing, because when you're just programming all day long, you end up getting fairly fast at programming because you're just in your zone programming. Let's see. So I probably want to have these guys, because I can click on this and I can type some stuff in here. But do I want to give myself? I probably want to give myself something that tells me which byte I'm dealing with, right? So maybe that would be a label. And I probably want to put that inside of a horizontal linear layout. Okay, so I'm going to give myself a view group. We'll call that guy row. And then I'll create a, what's it called, text view? Text view. Byte num, something like that. All right, so let me go ahead and create my row. So row will be equal to a new view group. Ooh, I don't really want that one. A new linear layout. Can I say horizontal? No. So we'll say new linear layout. So actually, I'll switch that to linear layout here. And I probably need to give this guy context. Do I need to get anything else? Nope. And then we'll say row dot, is it orientation? Set orientation. And then this guy's taking in an int, so I'm guessing it's going to be linear layout dot horizontal. That's my orientation for that guy. That way when I add stuff, they add next to each other. Okay, then I'm going to go ahead and give myself my text view and set it as memory location. So maybe just say 0, something like that. I think that's kind of what the book did. So we'll go ahead and create a byte num is equal to a new text view with that context. And then we'll say byte num dot set text, and the text is going to be equal to the empty string concatenated with I concatenated with colon. Something like that. We'll see how that looks. Okay. So that's going to be my byte num. Then we have our temp. Then we're going to go ahead and add these two things into my row. So we'll say row.add view. and we'll add byte num first, then row.add view. We'll add temp second, and then we're going to add to our memory layout the row. Let's see what that looks like. This isn't the highest performance thing in the world, but it will get the job done-ish.
Are these 8 bits or these bytes that I said?
Mm-hmm. It looks like my horizontal, I need to set up to match parent instead of wrap content for the width. Probably isn't a big deal actually, because we're only allowed to put bite-sized things in here. So actually, what we might just do, go ahead. You just set the gravity on it probably. I'll just take my linear layout here, and I'll set the gravity to center horizontally. Then it should just be in the middle. I think that should look pretty decent. Well, did it not finish running, or is that not the thing that had to have the gravity set? Now it's running again. I wouldn't think we had to set the gravity on the scroll view, but we might. Yeah, it looks like we can't set gravity on a scroll view. You can choose that center, but I don't think that's going to mean that'll suck it down into the middle. I don't think that'll make the difference. Otherwise, we're just not going to worry about it. Yeah, we're just not going to worry about it. Okay, so looks good enough. It'll get the job done for us. So now we need to go ahead and represent memory in core. So I need to go in here. So just like we had a bunch of register values, we're going to go ahead, we're going to create we'll still represent these things as strings because that seems to be the way. So now we're representing 256 bytes of RAM. So the smallest we can store is a single byte. So we'll say static string array. I guess we could just say RAM. This would be a new string array. And let's give ourselves a static int number of bytes in RAM. Set that equal to 256. So that guy will be number of bytes in RAM, like that. All right, so then we need to go ahead and initialize RAM. Throw a bunch of zeros in there initially. All right, so this initializes our registers. We'll create another function here, static void initialize RAM. this says for int I is equal to 0, I is less than ram.length I plus plus ram at bucket I is equal to 0. All right, and then when our main activity first launches, we'll go ahead and tell that guy to initialize ram. So we initialize registers. We'll initialize RAM. Okay. And now we need to connect those two. So on our RAM screen, we need to go ahead and fill up our RAM buckets with the right values. So let's go on to our RAM screen, and instead of saying 256 here, we're going to say core dot number of bytes in RAM, except probably better than that. Let's see, there we nailed it. All right. And since I have trouble typing, we're going to copy that. So I'll be able to copy it there. All right, so this code right here this generates RAM visual representation, something like that. All right, so then we want to actually go through RAM and fill it. So I have the memory, and the memory has the exact same, actually, hold on. I'm never actually putting those things in memory, am I? I'm not. So here is my edit text. So I need to go ahead and say this dot the memory at bucket I is equal to temp. I need to hold on to those edit texts. Right now, they're being contained visually inside of my vertical linear layout, my scrollable thing. Okay, but I also need to give myself programmatic access to them, so I'm just going to throw all of my edit text into my array called the memory here. And that array has the exact same number of buckets in it as my RAM has in core. All right, so those guys are effectively parallel arrays, just like we did for our registers. So we have 8 and 8 for registers. We have 256 and 256 for these. All right, so now we have given ourselves our visual representation. So we've loaded up our visual representation for RAM. Now we need to go ahead and initialize RAM with the values that it currently holds, right? So we'll go in here, and so now we'll say update memory with current values, something like that. So we're going to say for int I is equal to 0, I is less than core, oh, did I save that? Nailed it. I plus plus. All right, so now we're going to go through and we're going to grab from the singleton all the information into our RAM here and fill it in. Okay, so we're going to say that I'm lost. This dot the memory at bucket I dot set text, and that text is going to be equal to core dot RAM at bucket I. So whatever that holds, which is going to be a bunch of zeros initially, right? Okay, so I'll save that. And let's run this and make sure it shows up as a bunch of zeros while I grab another bite. Okay. We really should have more space. I'm going to do something here, just so you can read the numbers. I also want to make the text a little bit bigger. Byte num dot, is it set? Android text view set font size programmatically. Set text size. Well, I could just set the size given a float, so we'll just do that. Set it to 16. See what that looks like. So a little bit more spacing, a little bit bigger value. Oh, that's my registers. They still look beautiful. There's my RAM. Yeah, that's looking a little bit better. You could probably even go a little bit bigger on the number. So let's do 20. Looking sharp. Looking sharp. Yeah, it looks like it was probably 18 is what these are. But that's okay. We'll have the index be a little bit more. Okay, so we have our values here, and we have it offset a little bit better. Okay, and it's all filled up with zeros. So now we want to have it set where if I change one of these to a 5 and I hit save, it updates our RAM for us. Okay, so we're going to give ourselves our public void on save button pressed view v. All right, and just to make sure this guy is working, I think that's spelled right. So you can tell who's actually paying attention based on who laughs at my jokes. That's spelled right, right, Van?
Yeah, for me.
It's definitely right for Van. That's awesome. Okay, what was I doing? Oh, we're hooking up the button. So here, I need to show way less. Fewer attributes. Go to the on click, on save button press. Let's just make sure that guy is hooked up right. Go to RAM, go to save. I'll hit a couple times. Yep. Oh, spelling looks perfect there too. Okay, so button's working. So now we just need to write the logic for the button. All right, so this guy is going to go and take whatever the current values that are stored in memory and overwrite what those values are in core. So we're going to say for int I is equal to 0, I is less than core dot number of bytes in RAM, or we could have just said the memory dot length, or we could have said core dot RAM dot length. Didn't matter. They all mean the same thing. I plus plus. All right, so we'll go through all of our bytes, and we're storing strings in core. So we'll say core dot RAM. Yeah, so really, if we were being consistent with this, I'm going to go ahead and add our function in RAM to set a value at a position. Actually, maybe not, because right now, the way the offsets are going to work, let's not write that yet. We'll just write this. We're not being super consistent, but we are creating this in the same way we wrote registers. Just the way we use registers from our assembler perspective uses some functions that we wrote. So this is fine. So we'll say core.ram at bucket I. That guy's expecting a string. What string? This dot the memory at bucket I dot get text dot toString. So that will store up there the current version of memory. And then we'll do our little toast. Toast dot make text this, and then our message is RAM saved, and then it's toast dot length short, good enough, dot show. Perfect. All right, so now we should be able to go in, change memory, save it, go back, come back in, see the memory was changed. So those values, and it was 170 something. Oh, there's our 9. All right, so memory is now being saved. All right, so now we have what we need to do the loads and stores. All right, so go back in here. All right, so syntax for a load. So load takes something from memory and puts it into a register. Store takes something from a register and puts it into memory. All right, so this is our destination register for our load. Now, so this syntax right here is saying what? It's saying go to a base address and then offset it by this. Okay, so if x2, does it show us what x2 is equal to here? Well, we'll just, assuming x2 is 20, this should go to memory address 120. That's what we're loading in there, is memory address 120. Okay, because this is the base address, and this is the offset from that base address. This is kind of array syntax. Kind of shows us how arrays work in actuality. Go ahead.
Is that the bytes or the bits?
Bytes.
Okay.
So this is so this will be, for us, this will be either bucket 0, bucket 1, bucket 2. So what the base address in memory is. Although that's actually an interesting question because we are labeling our bytes. It's like, 0, this is byte 0, this is byte 1, this is byte 2.
Wouldn't you want that 0, 8, 16, or 0, 7?
It's a good question. Let's look at their similar and see how their similar actually does it. That will make ours match. Because they both can mean the same thing. It just depends on how the, when we say bucket 1, are we talking about the second full byte, or are we talking about memory address 8?
Well, right, because is that 100 bits or is that 100? Yeah.
Well, no, I'm pretty sure the 100 is bytes.
Are you sure?
Yeah, the 100 is going to be bytes. The real question is that base address, does it want to know which byte number you're on, or does it want to know the base address of it? So, for instance, byte 2 would be 2 in ours, but would be 16 in theirs.
Yeah.
So let's see how theirs works, and we'll just make ours mimic it.
Theirs goes by 8.
Well, I know that the memory does. So here, let's show, we'll show memory address 100 Let's show 80. All right, and we can load a direct value into a register, right? Is that still that? So we can say load into x2 an immediate value of 80. Let's just run that. We'll see if x2 gets an 80.
Isn't that offsetting by 80?
No, the offsetting by 80 should look like this. You know, that would be the value that's in one of these things. I want to see how do I just put a number? How do I do an immediate into a register?
Wouldn't it just be then x8? Well, okay.
What's the instruction? I effectively want to say x2 is equal to 80. That's what I want to say. What's the instruction in ARM to load an immediate value into a register? Anybody know off the top of their head? Otherwise, we'll go look it up.
I mean, if you scroll down past the simulator, there's some more like examples.
Okay. Of stuff?
Other stuff, yeah. Like the load.
Right.
Yeah, you passed it. Go up a little bit. There's some load.
Yeah, but see, this presumes that x3 already has a 4,000 in it.
Well, right, but don't you have to clarify that?
Well, yeah, so that's what I'm saying is they've just told us in here that x3 already has a 4,000 in it. So I want to know how do I get 4,000 in x3?
Oh, just plain, just nothing.
Yeah.
Else. Okay.
How do I initially put 4,000 into x3? Just a simple immediate value into a register. Because all these are making that assumption, right? Oh, move. Move, yeah, that makes sense. Move immediate, right? Well, move R. Okay, hold on. Does it show the moves in here? It doesn't. Let's go back to. Is there just one version of move that works for all the different kinds? Is this the one that has a list of all of our instructions? Next one? Where's our list of instructions? Is it 2.5?
Yeah. That you mean a table?
Yeah, at the bottom it has like 50 instructions or something.
Oh, not that huge
I want to say it was 2.4. It's right at the very bottom. Just a big chart of leg instructions. You know where it is, Edwin? Edwin found our last hidden thing in the book. Yeah, but where's the list? There's a list of instructions somewhere in here. I just want to see them so I make sure we give ourselves the right ones. It's got to be earlier than these. So it's got to be like in 2.3 or 2.2.
2.2, I think. That one? Oh, there is a big list here. 2.2.
Yeah. Okay. So this guy, move Z will move an immediate value into a register. So this loads a 16-bit constant with the rest being zeros. So this pads it with zeros, right? All right, so we need to go ahead and let's implement move Z to get us a value in there. But I think we already had the answer to our question where the base memory address is going to be something like 4000 or 4008, that kind of thing.
Is that typical that you start
No,
at like 4,000?
I think that is bits. He's right. That is bits, not byte. Because the example is you can see that load byte is saying x2, 40.
Oh, that does make sense. That makes sense because they had, if we said 4000, that's an offset of 4000 bits that takes you to that memory location, which I guess potentially could be in the middle of something. Do they allow you to offset in the middle of a byte? Like, can I load into here? Let's write this real quick, and then we'll go and test that because what I want to know
There's
is
something called load half. Load half here.
oh, which will then let us grab I guess it would be a nibble, so 4 bits, so we can offset any number of bits. We probably can. We'll test it, but we probably can break it then too by saying, look, I wanna load the byte that starts at bit number 6. So that'll get you bit 6, 7, and so the last 2 bits of the previous byte, and then the first 6 bits of the next byte, because you're kind of bridging when they stop and start. All right, well, let's do a move Z. That way we can put stuff into our RAM. All right, so move Z has 2 commands. One's a register. One is an immediate value. It does pad the rest with zeros because we're not storing in, well, ours will automatically be padded because we're storing a decimal value in there. We're relying on Java's internal representation of numbers. So we would not be able to do this move wide with keep, which will overwrite what's currently there, but not break any, like if you already had a bunch of bits in there that made up your 16-bit value, and you moved a number in there, it would only change those that actually needed to be changed. All the other ones will remain the same, whatever they were before. In the event that that was necessary, which if you're going to use a register to hold 2 values, that kind of lets you do the high and the low of that register. So you might decide you want to move into it a value that gives you the low 8 bits, not changing the high 8 bits because you want to leave them what they were before. We're going to have a tough time representing that in our simulator because we're using Java's representation of numbers rather than writing our own binary number system where we can have direct access to our internal bits. It's probably okay. It's not the end of the world. This does give us a limitation for our simulator where we're not going to let them change the internal representation of a number in case that was something they wanted to do. So move Z we can do. Move K we really can't unless we reevaluate how we're storing numbers. All right, so this takes a register and takes an immediate. So let's go and add this dude. So this is going to be in our main activity. All right, so we're always going to get an opcode, and we're always going to get the rest. Only if it's add I, sub, or sub I do we want to do all this stuff. Else if, and actually what I'm going to do here is I'm going to take our little toast from there. I'm going to put it outside of this guy. That way it'll always show us what opcode finished. All right, so now we're going to have an else if. And we're going to say opcode equals ignore case, and this is going to be move X, correct? Or it's move Z. Opcode dot equals ignore case move Z. If that's what we're looking at, then we expect 2 inputs. We expect there to be a destination register, so that's going to be an RD. Okay, so we already have that guy. So we'll say RD, and RD is going to be equal to the first thing when we split. So we'll do the same kind of split as we did here. So I'll steal this guy. So this will be parts at bucket 0 dot trim, just in case we need to trim it. All right, and then we have one more value, which is going to be our immediate value. So we'll put that in RM. So we'll say RM is equal to parts at bucket 1 dot trim. Okay, even though we're using verbiage like it's a register, that's where we stored our immediates before, so that should be fine. All right, so we have RD, we have RM. The command is move Z, which means we're taking whatever is in RM and putting it into. Now, actually, hold on, let me ask you something. Does move Z only support immediates, or can the second value be a register? Let's find out. That way we make sure we write it the right way. Only immediate? Okay, so we can't move Z X0, X3. Has to be an immediate. Okay. Rest was all of our comma delimited stuff. So we got our opcode right here. And then rest was like the X0, comma X2, comma X3. So that was everything other than your opcode. So then when I split that on commas here, for this example, that should give us our whatever the name of the register is in bucket 0, and then whatever the immediate value is in bucket 1. Because we're splitting it on commas. Yeah, so rest is going to look like something like this. X2 100, something like that. Now, when we load it in there, is it 100 or is it always like this? All right, so when are hashes used versus not used? All right, well, we do want to figure that out, but this one's just direct. Okay, so that means we're moving the integer version of RM. Actually, it is a string version since that's how our memory works.
No, actually in that table they did not mention hash for even add I.
Oh, it doesn't mention the hash value?
I think, but other example shows in the add I hash. So I think it also needs a hash.
So you think it needs it, or
I think it needs it.
or is it optional? Should we just assume it? Why don't we assume that all our immediates need the hash? Okay. Otherwise, we'd have to do it if the hash is found, then then get bucket 1 on. Otherwise, just convert it. It wouldn't be the end of the world, but we'll just assume all of our immediates have those values. Okay, so that means that I need to get. Well, we'll do it in 2 steps. So we need to go ahead and write the. We're loading it into memory. So I need to get the value from memory at a particular position. Although this isn't memory. This is loading into a register. So we have everything we need for this guy. So we're going to say core dot set value of register. What register? RD. What value? This guy is going to take an int value. And then we're having him convert it back to a string. So this is a little bit whatever. But so we're going to say integer dot parseInt rm dot substring from 1. So it'll get us past the hash symbol. So this gives us everything but the hash symbol. This will give us the numeric version of that we're then passing into set value of register. And the register we're setting the value for is RD. Something like that. All right, so that should be it for move Z. All right, so let's test this for move Z. I'll just give myself a new sample thing here. So I'm going to do move Z, and we'll say X5, comma, pound 100, something like that. That looks like a legal command. Okay, so let's run this. I'm telling you, this app could be a bestseller. I would say it's all pretty much as good. So, well, it looks like it's going to be on par with the simulator that's in the book. I don't know how much that's saying. All right, so go ahead and run this. Move Z is complete. So I should be able to go into my registers and see a 100 in X5. So there's my X5 and there's my 100. So now we support move Z. All right, now we can do loads, right? All right, so so now we need to, because load is going to take a syntax that is going to be, what is it, LDUR? Is that it, LDUR? So we're going to do LDUR, then we give it the destination, then we give it the square bracket syntax where we have base address, comma, offset. And offset, since it's an immediate value, is going to be have the pound sign in it, right? We decided all of our immediates will have pound sign. Okay. So let's go in here. So else if opcode equals ignore case and LDUR. Okay. So in this case, rest is going to look something like yeah, so something like x2, comma, then square bracket, x3, and then something like that. So that looks like what the rest should look like for us. All right, so when we split this on commas, we're going to get the register, and then we're going to get this syntax. So let's go ahead and do a split first. So we'll do string array parts is equal to rest.split on the comma. This guy is going to give us two pieces. It's going to give us RD, which is going to be parts at bucket0.trim. But then we need to go ahead and handle this part here. So in order to parse out this part here, we need to, oh, hold on, it's going to actually give us three parts, right? So we're going to get this, then we're going to get this, then we're going to get this. All right, so what I'm going to do here is we are going to remove all the brackets here. So we get three flat pieces. So we're going to try to turn rest into that before we do our split. Make sense? So before we do any splitting, I'm going to take this string, the string that currently looks like this, and I'm going to make it look like this by removing the opening square bracket and the closing square bracket. All right, so we can say rest is equal to rest dot, do we have like a replace? Yeah, so we'll go ahead and replace, well, that guy. Let's put a space in there. And then we'll replace this guy with a space. So that should give us this. So an extra space in those two places. Okay. So now when I do a split, this will be bucket 0. This will be bucket 1 with an extra space. This will be bucket 2 with an extra space. But we're doing trims anyways, so those spaces will be meaningless. So RD is that. Then we'll say RN is parts at bucket 1 dot trim. Then RM is equal to parts at bucket 2 dot trim. So that'll be our 3 pieces. And we're trying to store the value in RD of memory location, the value that currently lives in RN, plus the integer version of this guy. Okay, so we need to get the value of Rn, and then we need to get the integer version of Rm. So here, so we're going to do core dot set value of register. The value of the register we're setting is RD, and we're setting it to a location from memory. Okay, so let me just comment this out for a second here. So our location for memory is going to be the base address, which lives in Rn. So I need to get the value from that. So that's going to be core dot get value of register Rn, and that guy's going to give me a string. So I'll say integer dot parseInt of this string. So that will give me the base address as a numeric. What's that guy not happy about? Oh, does that give me the int? I thought core dot get value. Oh, it does give me an int. So we don't need to convert it because it already converts it. Perfect. All right, so that gives us the value of our register, and we want to add to that the numeric value that lives in Rm. So that is going to be integer dot parseInt rm dot substring 1. That'll convert that guy into a all right, but so that gives me the memory address of this guy. So we're going to say int mem address is equal to that. Then we need to go and look that value up in memory to get the byte that lives there. Correct? Okay. So let's pause this for a second. So we decided we do need to go and update our counters to go from to be multiples of 8, right? So 0, then 8, then 16. All right, so let's go into RAM activity. So we'll call this guy int byte counter. Starts off at 0. So we'll put byte counter in here, and then we'll say byte counter times equals 8. And plus equals 8. That'll be right? 0, then 8, then 16. Okay. Let's make sure that looks the way it should look. Zero, 8, 16, 24. So all the way up to memory address 2040. Look reasonable? Okay. So now we're going to say, now, are we making the assumption that the offset they're giving us is going to be a whole bytes? Because we decided that the offset they're giving us is in bits, correct? So are we making the assumption that that is that number of bits is evenly divisible by 8? Because like saying 100, like our current example here, this would, well, this is not the example we're looking at, but offset of 100 wouldn't work because that's not a byte-sized step. So we're assuming it's bytes. It's a multiple of bytes. Does it have to be a multiple of bytes? I don't think so. Because there is a version of, you said that there's a load half that will allow you to load part of it. So that means that you could have a step of a nibble.
Or even a byte. You can look.
Or a bit.
A bit, yeah. That's
No, our memory representation should be in bits. That will be perfect.
It's,
Is that how, but I don't think that's how the simulator is.
I'm looking into that one. Yeah.
Yeah, because the simulator, it goes from 0 to 8, which means that the first bucket is byte size, right? So it's holding bytes. And since we're not storing things at the bit level, instead we're storing things at the decimal level, I think we have to assume that your steps need to be divisible by 8.
well, right. I mean, when you're loading a byte, it's actually LDURB. It's not like.
Correct, but I'm thinking about their simulator.
Oh, just theirs?
Yeah, so otherwise, we can make ours better. We can do ours at the bit level, but then we'd have to represent our memory as binary. See, that's the challenge. The reason they made the decision for their simulator to hold bytes at a time is because they decided to implement theirs in a way where people could just put in numbers instead of talking in binary. So I think it's reasonable for us to make that same decision here, right? Especially since it's compatible with everything else we've done. We're using Java's numeric representation. All right. So with that in mind, so we have the correct numbering now, and we're going to assume that that offset that they're giving us is going to be divisible by 8. We won't check it. You better give us a number that's divisible by 8, otherwise things break. Although, maybe we should at least check that.
We can do divided by 8, whatever it they give.
Ah, yeah. So, well, hold on.
Not divided by 8.
Well, the mod 8 would say if it's equal to 0. That would,
Subtract mod 8. Subtract mod 8.
that way we can give them. We'll adjust their offset for them. Is that a better result, or is not letting it work a better result? Like, do we want to fix their input to what we think it should be, or do we let them know that your input wasn't a multiple of 8?
Or else fix it and prompt them. Tell them we have done for this.
Oh, we're not going to do both. We're either going to fix it or we're going to tell them they're wrong. Yeah. It's kind of funny. All right, so let's go. Well, it'll be a game time decision here. Let's decide what my fingers decide to type. Where are we going? Main activity. All right, so really, we need to so I'm going to say int offset is equal to this value. Then we'll say if offset mod 8 is not equal to 0, then we'll give them a toast, make text this dot offsets must be multiples of 8. So then what we'll say in here is we're going to say offset is equal to offset minus offset mod 8. Right? That's how our adjustment will work. Adjustment will be offset minus offset mod 8. And then we'll tell them adjusted offset 2 plus offset. Comma toast dot length short dot show. All right, so if they gave us an incompatible offset, we'll adjust the offset to a compatible offset, let them know we did that, so we'll give them a visual toast, and then we can move forward with their adjusted offset. Okay, so the memory address we're going to try to get the value from is going to be this base address and then this offset. Now, base address probably should also be a multiple of 8, right? Right now it's a register, but we do assume it's a multiple of 8 as well. All right, so big fun. All right, so this is going to be, we need to get the value of the register. Let's do that first. Reg value, or reg val, is equal to core dot get value of register. And this is going to be RN. That's our base address. Then we'll ask if regval mod 8 is not equal to 0, then we'll say regval is equal to regval minus regval mod 8 to adjust it, and then we'll toast them. Toast dot make text this dot base addresses must be multiples of 8. Adjusted base address to reg value. Then toast dot length short. All right. So that guy will only allow us to have legal reg values or offsets, and we will adjust as necessary. So by the time we get through here, we know that reg value and offset are legal values unless they gave us like a negative number or something like that. So there's still ways for them to break this, but they would have to grossly try to break it. All right, so then our memory address is going to be reg value plus offset. Now we need to get the value that lives at that memory address. All right, so this is going to be, so this is a multiple of 8. This is going to be a multiple of 8. So them added together, so if we have base address 0 and then the other thing is 16, we want to get the guy that lives at base at address 16, which is going to be our bucket 16 divided by 8, which is 2. Correct? So the actual memory address is going to be in, we have to divide this address by 8 to get us our address. So let's go into core. And we're going to say static int get value of memory, or get value at memory, address, and this guy will take in an int address, and we will return this dot, it's not this dot, it's just RAM at bucket address divided by 8. And that guy is a string currently, so we need to say integer dot parse int of whatever's in that bucket. All right, that look correct? Because what we're going to get here is, for instance, if we say that we want to go to base address 0 and we want to get offset 16. All right, that means that we want whatever lives at base address address 16. Well, in our array, that's bucket 2. 16 divided by 8 will give us the 2. Okay, because we do 1 byte jumps. All right, so we're mapping it to the correct bucket of our array. So this is bit-based address converted to byte-based value. That's effectively what we're doing there. Okay, so now we should be able to get the value at that memory address. So we're going to set value of register to core.getValue at memory address mem address. And that should copy something from memory into a register. Okay. And that's for LDUR. So let's test this. All right, so let's go ahead and we're going to move into X5. We'll give this guy a base address of 8. All right, so we did that. You can check out our registers. There's X5 with our 8 in it. All right, so now we want to go and put something in RAM. So, so base address, so if it starts at 8, and then we say we want to offset by 16. That'll take us to 24 here. So let's put an 11 there. So we'll put an 11 at memory address 24, which is base address 8, offset 16. So I'll save this. Then we'll go back. So now we'll do LDUR. And we're going to load into X1, base address X5, offset 16, like that. So X1 should have an 11 in it when this is done. So we're going to load into X1 the value that lives at base address X5, which is 8, plus 16, which should take us to memory address 24. Give me the value that lives in memory address 24, which is an 11, stored into X1. So run this, go to registers, X1 is 11. Woot. All right, then we'll go back to RAM here. We see our 11 there. This guy's still saved. That seems to work pretty well. All right, so now we need to do a store. So it's STUR. That's what it is, STUR. Okay, and that's going to take in the register we're storing, and then where we're putting it in memory. So we need a base address, and then we need the offset from that base address. Okay.
The simulation is breaking if you give non-multiple of 8.
It's breaking?
Yeah.
Mine's not going to break.
Not yours, Dave.
Oh, yeah, mine won't break.
Yeah.
And look, offsets must be multiples of 8. They adjusted it, and this should, I think, so 21 divided by 8 is going to have a, yeah, so it should adjust it to 16. So our RAM should still have, well, X1 should still have an 11 in it. Yeah. Crappy simulator they wrote. We should just send them our update. All right. So let's do LDUR, and then we will take a break, and then we'll go check out the mixed reality stuff. It's like a warm down, cool down. Okay. So LDU, oh, that's STU, right? STUR is what we're writing. Else if we're looking at STUR. All right, then if we're in there, rest is going to look like, so I'm going to, actually, let me just steal like a lot of this, and then we'll just update it. All right, so right now, rest would look something like that. We want it to look like this, so we can do this little replace thing again. So that's now the way we want it to be. So our RD is going to be our, we can say it's our destination, but it's actually the source value. Our destination is actually in RAM with the store, right? But we'll still store it in, we're still going to have our RD value, but we're going to have to get the value from that register here in a second. We're still going to need RN and RM because we're going to need those two guys. So this register value for RN is still something we're going to need. This is still something we're going to need for our register value. This is still something we're going to need for our offset. All right. So this is ultimately our memory address, but that's where we're putting stuff back to. All right. So all the math is right. Just we're putting it in different places. So instead of bringing from mem address into RN, we're going from RN and overwriting mem address. Okay? So now we need to have a function that sets the value in memory at an address. So static. Did we do set? We had Boolean before. Boolean, set value of memory, set value in memory, set value at memory address. All right, so it's going to be int address, and this is going to be int value. All right, so we need to take our address and divide it by 8 and set the value. So we will say, what was it, RAM at bucket address divided by 8 is going to be equal to value. That holds strings, so I'll convert it to the string version of that value, and then I'll just return true. That we successfully stored it in case we care. In case later on we want to add some error checking to storing in memory. All right, so that sets a value in memory. So go back in here. So we now need to get the value from RD. Int value to store is equal to core.get value of register, whatever is in RD. And that's the value we're going to store. And then we're going to say core.set value at memory address. What address? Mem address. What value? Value to store. And that should be STUR. Okay, so let's go test that. So we need to, let's just run it. I'll figure out what we need to do to test it. Okay, so we're going to go ahead and let's just put in x1 the number 25. We'll save that. All right, and then let's say, well, we could just go ahead and put something into, we'll say x0 is 16. That'll be our base address. That way we don't have to move z into that. So we'll save that. So now we want to store in memory at base address x0 plus 16. That'll put us at address 32, the value that's in x1. Reasonable enough. So that should put a, what was it, 25 was an x1? So 25 should be in memory address 32 when this is all said and done. So STUR, value we're storing is x1, right? That's where the 25 was. And we're storing it at memory address, base address x0, offset by 16. So that should put at memory address 32 the number 25, which is stored in x1. And 32, there's my 25. Woot. All right, so we've done quite a bit of damage. So now we got, we got adds and subtracts. We can move immediate values into registers. We can load and store into RAM. It's already a pretty legit simulator, right? All right, so let's check this in. Commit changes, added, add I, sub I, move Z, LDUR, and STUR.
Would like the best way to do this eventually is like for each one of those have a separate function?
Probably, just so you don't have this monolithic if, but I mean that's only gonna take a few minutes to do.
Okay, I didn't know that's the way to...
Probably.
Probably, okay.
Yeah. Although I'm not, since we're doing it all inside of one class, I'm not sure it necessarily buys you a whole bunch. I mean, you're scrolling either way. And the advantage right now is doing it all in here. We have access to our initial command string so we have opcode and we have rest. Otherwise, we're going to be passing that into these other functions. So the other functions would actually be more memory inefficient to do it, but it would be more subdivided so you can change stuff in different places rather than your subdivisions being inside of an if statement.
Okay.
I think by nature, assemblers are probably just messy looking.
Okay.
I think that's probably a truth. Okay, so let's stop. Well, so let me go ahead and tell you what I want you to do for next class in terms of reading. I'm not going to give you a regular assignment. So next week is undergraduate spring break, so I won't be here. I'm going to be out of town, so we won't meet next week. So the next time we'll meet is 2 weeks from today. I'm going to give you some reading stuff to do in the book. So right now we've done up through 2.7. That look right? So we want to do procedures, 2829. I don't want to have to do that much. 2829. So let's do 2.8 through 2.12. That shouldn't be very much, like in terms of time. You should be able to spread that over 2 weeks pretty easily. So read 2.8 through 2.12 for next class, and that's 2 weeks from today. So let's take about a 10-minute break or so, and then I'll show you guys the mixed reality stuff. If you're not interested in the mixed reality stuff, you can take off, but I'll stick around. It's actually kind of cool if you want to think about how Windows can work using VR, effectively VR. But, you know, mixed reality is kind of neat, so I would encourage you to stay, but if you want to go, I'm not going to chase you. All right, So back here, let's just say 9:30. We'll meet in here for the look at the VR stuff.